Our method is inspired by the paper called Vision-Based Obstacle Avoidance Strategies for MAVs Using Optical Flows in 3D Textured Environments. The authors run Farneback dense optical flow and mainly use the magnitude and the expansion rate of the optical flow to decide when, which direction, and how quickly the MAV should turn. The fundamental ideas are, first of all, if the expansion rate is large, then there is probably an obstacle ahead. And secondly, the sum of the magnitude or expansion rate of the left half plane is large, then the obstacle is more likely to be on the left hand side, so the MAV should turn right to avoid it. We thought this would be really useful as it eliminates the need to tune color thresholds, which may change due to different lighting conditions. So we soon started comparing the runtime and the effect of different kinds of dense optical flow algorithms in Python. We tested all of the algorithms provided by OpenCV. We discovered that the Farneback cannot calculate the optical flow of textureless objects, for example the black panels, but other algorithms do not have this problem. Among the algorithms, the dense inverse search, or DIS, method is the fastest, so we decided to use DIS as our optical flow calculator. On the Bebop, it can run at 25 frames per second on 200 by 40 images. Now you're seeing how our method works in the simulation environment. We created our own flight plan XML to make the user interface more interactive. We added a waypoint as a goal, it can be dragged, and as soon as the start button is clicked, the MAV will try to fly towards it while avoiding obstacles including the orange poles and panels. We also added a button to toggle whether the goal is auto-generated and constantly updated, or it is manually given and remains static. We found a way to visualize the frames using OpenCV IMShow by compiling the OpenCV project with GTK flags and adding additional links to our target, so here you can see the images used for debugging. Plus, we added a telemessage that contains visual detection results. These results can be conveniently plotted using the plotter tool. The plot on top is the sum of expansion rate, and the one below is showing the raw and filtered difference of flow magnitude of the left and the right half plane. Then, I'll explain what's going on as I click Start and turn on Auto-Generate Waypoint. Now the generated waypoint is straight ahead. The MAV is already facing that way, so it accelerates, enters the constant speed phase, and starts looking at the sum of flow expansion rate. If the expansion rate goes above a threshold, it brakes and moves a bit backwards to free up space for turning. Then it turns according to optical flow results, geofence information, and trajectory history. Afterwards, it turns to the goal again and repeat the above steps. During the acceleration phase, the expansion rate is huge, so it isn't used for obstacle detection. So you might wonder, what if it bumps into the obstacle during that period? Well, it is a short period and we check the image gradient before accelerating. If the gradient is below a threshold, meaning that there is a close-up obstacle, then the MAV actually goes back a bit and turns instead of going forward. The last back off and turn was due to low gradient value. A new waypoint is generated if the previous one isn't reached for a certain amount of time. You can see it is going to a new waypoint. This prevents the MAV from trying forever to reach an impossible position. Now, there's a pole straight ahead, and you're about to see how it detects it, brakes, goes back, turns, and finally completes avoidance in satisfactory smoothness. In our design, either the waypoint isn't hit for too long, or it is hit, a new one will be generated. Now, let me manually set the waypoint to test some corner cases, which demonstrates its ability to stay in the zone while avoiding thin panels and at the same time going to the desired position. For this part, let me just speed up the video to save some precious time. As you can see, it is not the most effective strategy, but at least it works. To be honest, we tried our best to make the tuning process painless. We made use of the DL setting framework so that the thresholds, the velocities, and control parameters all can be tuned in flight. For example, let's try setting the PD heading controller's P gain to 0. So as you can see right now, the MAV is hardly turning at all. The angular velocity recovers if we set the P gain back to a reasonable value. So to wrap up, I think it works pretty well in the simulation, but I must admit that it doesn't work well in the reality yet. The real MAV's control system performs worse, which makes our program constantly pick up large optical flow values. In addition, the real images contain more noise. There are tons of factors contributing to the sim-to-real gap. And all of these require us to tune the program specifically for the real world. But unfortunately, we didn't have enough time. We encountered 2 broken drones, we had to share the CyberZoo resources with other groups, also the batteries died really quickly. Anyway, everything was so inefficient, and we've tried our best. We learned a lot, especially the way to deal with extremely resource-constrained robots. I do personally wish we could have more powerful MAVs and implement state-of-the-art algorithms, but in general, it was a great experience. And I'd like to thank professors for giving the lectures, TAs for answering the questions, my group members for contributing, and anyone who helped us along the way.